Today we are going to talk about wave function and their importance and significance in quantum mechanics. So we start with the basic concept of probability. We have a group of 14 people whose age lies between 10 to 26 years. And we denote the number of people having a particular age is small j as capital N. So capital N is the number of people whose age is small g. So we see from this diagram, either the bar diagram, that the age 14 is of one person. One person is having age of 15 years. Three people are having age of 16 years. Two persons are having age of 22 years. Two are having age of 24 years. Five have age of 25 years. So when we are going to write number of persons whose age is 14, it is 1. Number of persons whose age is 16 is 2, 3. So it is 3. Number of persons whose age is 23, we see there is nobody, so it is 0. So now if we sum all these kind of numbers, we get the total number of people inside the room. Now let's go to the concept of probability. Like we have seen, there is only one person in the group whose age is 15 years. So out of 14 persons, one person is having an age of 15 years. That means the probability that a person will having an age of 15 years is 1 upon 14. So the probability that a person's age is small j is nj upon total number, that is capital N. And if we sum all the probabilities, the sum of all the probabilities is going to be 1. So the results can be generalized continuous distributions. A probability that a certain quantity will be having a value between x and x plus dx is denoted by rho. So rho is the probability density, and we can calculate the probability between the limits a and b as the integration between these limits of the probability density over dx. So this the probability in the limits a b is an integral in the limits a b of the probability density over dx. And if we do this, perform this integral from minus infinity to plus infinity, we get the universal probability, which is always 1, if the particle exists. So yeah, up to the end of the 19th century, the classical physics was not able to explain the black body radiation, the photoelectric effect, the Compton effect, and the spectral lines of the hydrogen atom. Some other phenomena occurring on the atomic and subatomic scales could not be explained through classical physics, and they can only be dealt with in the framework of the quantum physics. Although we have developed the classical and quantum physics quite extensively, but we don't have a satisfactory theory unifying the quantum physics and the classical physics. So, after the postulates of Einstein, Planck, and Einstein, it was concluded that the electromagnetic wave appears to consist of particles, which are photons, and the energy of these photons is given as h nu, where nu is the frequency, And the momentum of these photons is h cross k. Light behaves simultaneously as a wave and as a flux of particles. Light travels in the form of wave, but is absorbed or emitted in the form of a stream of particles. So the wave enables the calculation of the particle-related probabilities, like when the photon is emitted, the probability of it striking the screen is proportional to the intensity, which is in turn proportional to the square of the amplitude. So in turn, we can conclude that the probability is proportional to the square of the amplitude of the wave. So the wave particle duality signifies that the probability of finding a photon at a particular time t at a current location r is proportional to the square of the amplitude of the electric field. Since the information about the photon at the time t is given by the electric field, which is a solution of the Maxwell's equation. Now, the wave properties of the particle, of the electrons in a specific, we are confirmed by the Davison and Germer experiment. From their conclusion from their experiment that the spectrum is not a continuous one, it's a discrete spectrum. And the wavelengths of the electrons can be calculated from the diffraction data agreed with the expected de Broglie wavelength. So in quantum state, we are going to describe the object by a state, not by a particular trajectory. We are talking in terms of the state of the object. And the state is characterized by a complex wave function xi, which depends on which is a function of position and time. And the wave function is interpreted as a probability amplitude of the particle's presence. And the square of this wave function is proportional to the probability of finding the particle at a particular position and at a given time. We see that the square of this amplitude is given as the wave function multiplied by its complex conjugate, and the resultant is a real quantity. So the wave function is a complex quantity while the probability is a real quantity. And the probability density of finding the object at a time t inside the elementary volume is proportional to the square of the wave function multiplied by the volume element. So let us consider a one-dimensional system when the probability of finding the particle between the positions A and B at time t is given as the integral with the limit A to B, the square of the wave function with respect to dx. So the particle should be somewhere in the limits minus infinity to infinity of the probability density, which is the square of the wave function, and it will be 1. If the integral in the limits minus infinity to infinity of the square of the wave function is 1, we say that the wave function is normalized, and it is called, the process is called normalization. If this integral is 0, then the particle does not exist at all. We can see this probability in diagram. One is a wave function, one is the complex conjugate. The complex conjugate traverses in the inverse opposite direction as the wave function. You can see how the wave function behaves. And the probability is in this region, from this limit to this limit. Afterwards, in 1926, Schrödinger proposed an equation of the wave function. So that is considered to be the equation of motion through which the matter waves change in space and time. And this equation is a key element in the quantum mechanics. Superposition principle applies to the equation, and in one dimension, the equation takes the form. So this is the equation of motion governing. Now we can see this is the wave function, green one, and orange is the energy operator. We will discuss this in our coming lecture, how the energy operator varies with the wave function, when we will discuss the Schrodinger equation in detail. So today we just had a talk about quantum mechanics, or the basics of quantum mechanics, that is the wave function. We defined a wave function and what is its significance in terms of the probability of finding a particle at a specific position and at a given time. And we will be discussing the Schrodinger equation in detail in the coming lecture. Thank you.